The first homework assignment covers a basic concept of pulse shaping with the root raised cosine pulse shape. So I'll start by giving you an overview of the assignment, and then I'll be taking you through the software. So first, we'll start with what is an ideal signal. Suppose we had a perfectly rectangular pulse, and here is a sequence of pulses. We can see we call the time of 1 bit here. And then here there are several 1 bits in succession, logical 0 bits, etc. Now suppose that I was going to trigger my oscilloscope on the time of 1 bit and have it superimpose all of the bits one on top of the other, so that this time duration here that I see in this second window here is exactly 1 bit, whereas here there's maybe 20-bit intervals that are covered. Since these are perfectly rectangular, when I superimpose them, I will see the sort of infinite rise time here, infinitely fast rise time, fall time here, and some will be 1s and some will be logical 0s, and they'll all be superimposed, so I would get something that looks like this. Now suppose that I did not have perfectly rectangular pulses, but instead there was some finite rise time to them. So that same sequence of bits might look something more like this. So this would be a non-ideal signal. And if I did a superposition of all of these, this sequence of 20, one on top of each other, I might get something that looks more like this. So we call this the upper rail for the logical 1 and the lower rail for the logical 0. And I'll see some rise time here. And I've indicated here the time of 1 bit. So what we're going to be talking about today is how we can use an oscilloscope in a virtual laboratory to look at this superposition, which we call an eye diagram. So the eye diagram is a useful tool for assessing the quality of the transmission that we have. So this is a way of measuring our performance. So this would be a typical eye diagram. And in this typical eye diagram, we have a number of quantities which have been indicated here. So, for instance, this part, why do we call it an eye diagram? We call it an eye diagram because it looks physically like a human eye. And so here would be like the shape of an eye. And we even talk about the eye opening because there is a clear area here where there is no signal. Here we have the rises, we have the trace of the voltage, but mostly at the center of the eye, we would either have one of two values, either a logical 1 up here or a logical 0 here. The fact that these are not individual points, but instead have some thickness, could be due to a number of factors. It could be due to additive white Gaussian noise, and it could be due to intersymbol interference. So when there are various measurements that we can make in the eye to quantify the quality of the signal from this very simple measurement technique. For instance, there's part of the eye opening, which we refer to as the noise margin, the noise margin, and some other measurements that show what the sensitivity to errors and the timing might be in our signal. I'll notice here, I'll remark for you here that there is a border put here, which I call the optimum sampling time. So if I want to get the fewest errors I can in my transmission, what I'll do is I'll look at the eye opening, and at the maximum of the eye opening, that's where I'll set the sampling time for my linear sampling receiver. So this is when I would do my sampling, is at this instant. So in this homework assignment, we'll be looking at, in a virtual lab, some eye diagrams and qualifying the quality of the signal. And we'll be doing that using some pulse shaping with different kinds of parameters. And we'll see how these performance metrics change as I change my choice in the pulse shape that I'm transmitting. So I said that this was a virtual lab, so we're going to be working in a simulation environment, in particular in MATLAB. So in MATLAB, I have a simulation where I'm going to generate random data here. I'm going to take this random data and put it through a realistic root raised cosine filter. I'm going to add to that a certain level of noise, and I'll be varying the level of noise throughout the homework. And here at the receiver, of course, I would use a matched filter receiver, so I would have another filter, which is identical, another root raised cosine filter. Then I would have the received signal here, which would be inside of my linear sampling receiver. Now, the virtual lab part is that I'm going to assume that I have a real-time oscilloscope in order to look at the time traces from this virtual system, and that I have a spectrum analyzer where I can look at the frequency spectrum. In fact, today, these two devices really are sold as one device, and that would be a real-time oscilloscope where I could take the FFT, the fast Fourier transform of my time domain signal, and generate a frequency spectrum from that. So in our case, we're going to be using software produced by Agilent, now known as Keysight, and it's called VSA software, which is for vector software. I'm not sure what the acronym is for. But this is software which is available in the lab that we use in order to control our real-time oscilloscope captures. So this would not be atypical. So this is a virtual lab, but it's very similar to what you would experience in the laboratory. So the particular example that we'll be working on in this homework assignment is to use binary phase shift keying, so BPSK signal. We'll be simulating a transmission rate of 1 kilobit per second, and we'll be sampling this signal, so our real-time oscilloscope can capture 20 samples per bit, and that is the information that we'll be generating. So in MATLAB, we generate a signal with these characteristics, and we output a file which has 20 samples per bit, and we take that file and we put it as the input to this analysis, vector signal analysis, I remember now, VSA, into this analysis software. So let's look at what is the theory behind this first homework assignment. And of course, we've seen that the root raised cosine is a Nyquist pulse. Well, it's not really a Nyquist pulse, but once I combine two root raised cosine filters, they make one raised cosine filter, which does provide a Nyquist pulse. And that pulse is 0 at 1-bit time intervals. And what we'd like to look at is what is the impact on the eye opening of the choices I have in my Nyquist pulse. In particular, I'll be looking at several different roll-off factors. So for instance, here are 3 examples: 0 roll-off, 0.3 roll-off, and 1 roll-off. And we know that in theory that means that the bandwidth occupied ideally would be 1 kilohertz. So that would be if I were using a sync pulse. And if I used roll-off of 1, I would be doubling the ideal occupied bandwidth to 2 kilohertz. But in return for a higher occupancy rate, I would expect to have greater robustness to timing errors, for instance. So in this assignment, we'll be looking at these trade-offs. And think about the bandwidth expansion factor that is implicit in this use of a roll-off. So the bandwidth, for ideal signaling would be 1 kilohertz. Roll-off of 0.3 means that I'm adding 30% additional bandwidth, so become 1.3, etc. So what's the reality? That's sort of a shorthand of what's going on. But now look at the signals, what we look at. Well, let's start with an ideal raised cosine pulse. Here we have the case of r equals 0, where we have sync pulses in the time domain. And here is r equal 1, where we have a different roll-off factor, let me say. So when I say this is ideal, what do I mean when I say ideal? Well, first of all, there's no noise in these measurements. And secondly, it's infinite time support. Of course, this is very not physical, but a sync function has infinite support. And when I plot these, I used a MATLAB routine where, you know, the filter was really, really, really long, and it was almost like a perfect filter. In fact, when we truncate things, things will get a little bit more approximate. But this is the ideal. So here's another example of some traces that I have captured previously about the eye opening and the kind of traces that you'll be looking at in your software. Here I have, for example, an SNR of 35 dB, so it's a very, very low noise, high signal to noise ratio, but I'm using a finite filter length, and because of that, we can see a difference between the eye opening due to this finite filter length. So not so much the noise, more the finite filter length given these choices. So these are some measurements that you'll be asked to do on the homework, and I'll be talking about them a little later. So you can see that although the noise is really low, we can see that there's not a perfect point here with R equal 1. It looks like at the sampling time, you know, I'm getting zero contributions from previous pulses, very low ISI. But here in this one, I am much more subject to ISI, probably because of this truncating due to the filter length. So we'll be looking at measuring the bandwidth. And the bandwidth measurement, we'll see that there's a couple of tools in the software that allows you to quantify a bandwidth. One of the first weeks of class, we looked at different definitions of bandwidth, and the definition that you can use in the software is called the OBW, and this is one where you can specify the percentage of power inside of the bandwidth. So for instance, if we wanted to define the 99.5% occupancy, so the occupied bandwidth, you could ask the software to calculate that for you. Now we can see here also that there is something I would call the, let's say, absolute bandwidth, and that's here. You can see there's sort of a noise floor that's visible here. And when the signal gets down into the noise, somewhere around this level, so I might call that the absolute bandwidth, because I can sort of see where the bandwidth, where the signal sort of disappears. But if I looked at, there's not much energy in that last fall off. This is, of course, on a logarithmic scale. And so when it looks for the 99.5, it's showing me a bandwidth, which is highlighted in blue here, which is somewhat narrower than what I would call the absolute bandwidth. And absolute isn't an approximation, but let's say what you can see by eye as being pretty much outside of the noise floor. So if we looked at what is the 99.5% bandwidth, we can see that it is somewhat different than the theory would have told us. And that is because if we look here, you know, the roll-off factor maybe adding 30% to what we would call the absolute bandwidth, but there's actually very little power in that section. And so this gives you an idea of these different measures of bandwidth. So that's one of the things would be contrasting, would be the 99.5% bandwidth and what we would call the theoretical bandwidth of the absolute bandwidth. So that'll be something you'll be reporting in your homework. So here we are again at the simulator, and recall that there's part of this which is done in MATLAB and part of it which is in this analysis software. So you'll be running two softwares in order to see the effects that I'm talking about. And in the MATLAB in particular, we'll be looking at the effects of the roll-off. So I'll be choosing the roll-off that I use at my transmitter and at my receiver. And we'll be trying multiple values so that we can contrast them in the homework. And then once that's done, then I'll save a file, and that file will be going into the analysis software where I can sort of see perhaps the effect of truncation and delay for different roll-off factors. Also in the MATLAB software, we'll be specifying the SNR. I can put in various levels, and so that will be one of the parameters, again, that I run inside of the MATLAB. So you'll be reporting different parameters, and the first thing we'll do is we'll do it for fairly high signal to noise ratio. I put here 35. There'll be some other value in the homework assignment. There'll be particular values of R, and it could be different. It varies from year to year. But what I'd like you to do is to use the analysis software to start with a very high signal to noise ratio in order to measure the bandwidth. And you'll see that the higher the signal to noise ratio, it's not surprising, the clearer it is to delimit the signal from the noise, and so you can make a more accurate assessment of what the occupied bandwidth is. So we'll be looking at bandwidth, which we'll concentrate on during the high signal to noise ratio, and then we'll also be taking some values which are measured directly from the eye opening, and I'll be talking a little bit more about what these values are. But there's something that when you observe the eye opening, you'll be able to measure that with it. And of course, when we change the signal to noise ratio, the bandwidth really shouldn't change, but these values will change because they'll be influenced by the noise level. So in this section, we'll start adding noise to putting in different levels of the signal to noise ratio, and so we'll expand the table of what you have to report. Now, during in turning in the homework, I'm going to ask you to record several screenshots, because in order to fill out this table, you're going to have to say what is the bandwidth. And to do that, you're going to look at the screen. And on the screen, it's going to be reporting down here what the OBW is, written very small here, but we'll look at it on the screen. And I want to see that. So I want to be able to see when I'm grading the homework, what it is you saw on the screen, and from that, what you interpreted as, you know, the values that should go into this table that you're reporting to me. So I want to see both the graphics and what you report. And one will be the spectrum, and the other one will be the eye diagram. And when you do give me the eye diagram, I want to make sure that you understand this concept of what is the best sampling time. So I'd like you to indicate on the screenshot, put a line in there, tell me where you think the best sampling time is. For instance, here, I would look at the maximum eye opening, and in fact, it's important to look at that sampling time because that's where I should place my markers, which will be used to make some of those measurements which are reported in the homework assignment. So after you've made your measurements, then I'd like you to interpret your results. And so we have some discussion in the homework assignment. And in particular, I want to discuss what is the impact of the roll-off factor. So we're going to take a very high signal to noise ratio so that the noise is not getting in the way of what we're looking at. And we'll try various roll-off factors. And what I'd like you to do is, I said, save the screenshots, and this is where you're going to put it. You're going to put a label on, saying what the SNR is, what the roll-off factor is. Then you'll put the spectrum graph there. And then you'll put these two bandwidths, and you know, they'll be different, and here they'll be different, and then you're going to discuss what's the effect of the roll-off, what's the effect on the spectrum, for instance. What's the effect of the R factor on the eye diagram? And so here again, same parameters, but now I'm putting in a graphic of the eye diagram, and I'm putting in the quantities I measured off the eye diagram, and these can be compared to say what is the impact of the eye diagram on the time domain behavior captured in the eye diagram. And of course, in the previous one would be on the frequency domain behavior, which is captured in the spectrum. The next sections are about a little more general. What are the benefits, disadvantages of varying the roll-off factor? So you've been able to see what is the effect, and now we're going to discuss, are those effects good or bad? How are they good or bad? And then finally, we're trying to distinguish between noise and roll-off factor. How do these two things, how can I see them in particular in the time domain eye diagram? And how can we distinguish the presence of noise versus the presence of intersymbol interference? So this is the discussion that will make up the final part of the homework assignment. So again, this is the simulator. We've talked a little bit about what was going on in MATLAB and what it is you want to look at with the VSA software. And now in particular the VSA software, I'll be taking you through it in the example now, but I would like to just mention that when we open that software, you're going to have to give it, first of all, a setup. And the setup is really a file which basically tells VSA that this is the kind of system I'm using. It tells it that VSA that I'm looking at BPSK, I'm looking at 1 kilobits per second, I have 20 samples per symbol, etc. So that's in the setup file. And I also have to recall the recording, and the recording is like the captured data from your experiment or from your measurement, and of course that would be generated by MATLAB. So in the VSA software, I will load one file, which is the setup file, which is the same for all of the variations, and then I will be running MATLAB for each one of the examples. I'll be running it for a specific signal-to-noise ratio and a specific roll-off. It's that ordered pair, roll-off and signal-to-noise ratio. I'll be looking at the file generated by MATLAB. Now, once I have loaded these files into the VSA software, there are a couple adjustments that I'm going to have to make, and one of them is to something called the digital demodulation properties, and that comes under the tab which is measurement setup, and we have to make sure that the setup really is BPSK, 1 kilohertz symbol rate, and we want to put in our 20 points per symbol, and then this result length, and this is how many symbols will be presented at one time on the screen. And we want to look at something between 40 and 200, and I'll be talking about what different values you'd want to use and why. I want to mention that here sometimes the software is buggy, and you would like to be able to change the result length here, and sometimes you'll enter a number and it won't change anything. And if that happens, close the software, start it again. Usually that's enough to get by this bug. Sometimes I change the order that I load these files in. First I load the recording, then I load the setup. Maybe that'll help get over this bug. I'm very sorry about that, but if you cannot change the result length, then just go through those couple of steps. We'll see if it happens in my going through the demonstration with you. So the sampling should be taking place at the maximum of the eye opening. Very important to mark that because that is where you should be putting your markers. It should be at the maximum of the eye opening. And now these are for your first set of X's, and the other set of markers, well, then we look at where do we make our decision threshold. And we should set the threshold at the midpoint of the eye opening. So to make the fewest errors possible, we see, well, this is the segment between these two X's of the eye opening, and at the exact midpoint, this becomes my threshold for decision, and then at those are where I define the X's now for the other markers. So you look at the eye diagram, you put in some line that indicates to you what is the maximum of the eye opening, and then you set your markers X along this line. And of course you set the threshold and set up your markers X along that virtual line. So now we come back to the quantities that we're going to want to measure. And as we can see here, there's a measure of what they call the peak ISI. So we'll have two markers here, X and X, and then this distance here will be the peak ISI. We can see here the timing jitter is measured, and it will be between the markers that we put at this point. And all in all, here are the definitions of the quantities that are going to be reported in the homework assignment. And if we look at our textbook of SCLAR, there will be in the textbook some definition for these terms commonly used in the industry. And so you'll be putting in a total of 6 markers distributed in this manner. And then the quantities on the noise margin, the jitter, the sensitivity to timing, all these are taken as measured from these various markers. And you can see the equations here. And so you can have, as I mentioned, the software measure, for example, the difference between B and C, the difference between A and B. Those would be differential or delta markers that we'll be looking for in the software.